Hello class, and welcome to today's video on Introduction to Continuity, which is from Chapter 1, Section 7 of your textbook. You are responsible for watching the entire video, and you are responsible for taking any notes that you need to take. As well as at the end of watching the video, you are responsible for summarizing the video and coming up with a question either that you have that you don't understand from the video or that you feel would be a good quiz question. And you're going to submit both the summary and the question via the WISC form that you already have the URL for. So let's get started with the video. So here we have three different functions that are graphed, and as you can see, it's easy to identify which of the functions is continuous because from what we know of continuous functions, I can draw this function without having to pick up my pencil and moving it to a different location. So in other words, I can draw this function without any gaps or holes. So this is a continuous function. But if I go over here, in order to draw this function, I have to, after I draw this part, I have to literally pick up my pencil, move it to another location to finish drawing the other part. So this is not a continuous function right here. Over here, to draw this function, the same thing. I can draw without picking my pencil up to a certain point, but then I literally have to pick my pencil up and move it over here, and literally have to pick my pencil up again and move it to a different location or to completely draw the graph. So this graph or this function is not continuous. So it's easy to see that functions that have asymptotes or functions that are step functions with holes, as we see right here, are not continuous functions. But today we're going to look at more specifically a special type of function. A special type of continuity for which all of these non-continuous functions can be continuous to a point. Well, not to a point, but on an interval. That's a math joke you'll figure out a little bit later. So we're talking about continuous on an interval, and we're going to use the intermediate value theorem to define what it means to be continuous on an interval. So here we have, suppose we have a continuous function that's continuous on a closed interval. And the reason why it has to be closed is that we have to be able to evaluate the function at the endpoints of the interval. Because the intermediate value theorem says if I have a number k that is between my function evaluations at the endpoints of the interval, then there's going to be at least one number c that's in the a to b interval that you can evaluate the function at that point to get k. So I know that may be confusing written, but let's take a look at this picture below. So here I have a lovely, lovely function. Well, it's really not that lovely, but it's cute enough. And so here we have this function, and something could be going on over here. Like this could be the other part of the function. Who cares? And so we have this a and this b that's part of the domain. So that's our a and b, and we can evaluate the function at a, and we can evaluate the function at b. And so what the intermediate value theorem says, since f is continuous, then there's going to be some k in between f of a and f of b, so that, let's see, f of b, anywhere in between f of a and f of b, I can pick any value, and in this case, we're going to pick this value and name it k, and then the intermediate value theorem says that there is going to be some value c somewhere in this area such that f of c will equal my k. And that will happen for any value between f of a and f of b. You're always going to find a value c in the interval a to b such that f of c is equal to that value k. And if you can't do that, then that means the function is not continuous. So we're going to use the IVT to prove that something is continuous. Well, how will we know for sure where that value c is? That's probably one of the questions you're asking. Well, let's keep changing the value of a so that it's closer and b and closer together, so that it gets to the point where you can eventually find out that K, as long as K, I'm sorry, eventually find that C. So I hope I did a good job explaining it. If you have any questions, it would be a perfect time to include that into your whisk. So this is by definition how we consider functions that are improved functions to be continuous, because on a closed interval, by proving that no matter what value you pick in between f of a and f of b, you will always be able to find a c such that f of c is equal to k. All right, that's it for the video.